Good. Good afternoon, friends. Myself Manoj Kumar. Today we will discuss Rankine cycle. So Rankine cycle is an ideal vapor power cycle, but let us consider how it is developed. Let us consider Carnot vapor cycle. Since Carnot vapor cycle is benchmark cycle, so let us discuss what are the problems in Carnot cycle, why we are going for the Rankine cycle. So let us consider simple Carnot cycle having four components: boiler, turbine, condenser, and compressor. Uh, Let us consider the two processes in the TS diagram. Let us process 2, 3 and process 4, 1. These are the reversible isothermal process, and process 3, 4 and 1, 2 are the reversible adiabatic processes. So let us discuss the objective. What are the objective? So the objective is to design an optimal vapor power cycle. So what is the ideal vapor power cycle? So since Carnot cycle is an ideal cycle, so let us consider the two cases. The first cases is the Carnot cycle, the cycle A and cycle B. Cycle A, let us consider a cycle where the two reversible isothermal processes are done in the boiler or condenser in heat exchanger. So in the cycle A, let us consider a process 2, 3 and process 4, 1 are done in heat exchanger. So there will, it seems there is no problem in these two cycles, but in the process 3, 4 and 4, 1, since the expansion started process point 3, so what will happen after the expansion? There will be excessive moisture. So at point 4, the moisture content will be much higher than the recommended level. Recommended level of moisture content is 15%, or we can say the dryness fraction cannot be less than 85%. So this is the problem in this one. And the second problem is we cannot stop the condensation at point 1. Even if we stop the condensation at point 1, so it is impossible, or it is almost impossible to compress wet vapor up to 0.2 to saturated liquid. So it seems impossible to realize this cycle, the cycle A. So let us consider another cycle, cycle B. So in the cycle B, let us think that we are removing process 1 to the problem in process 1 to here we are compressing in the superheated region. So it will be quite impossible to compress up to 0.12. That the 0.2 is the here it is its temperature is above critical temperature, so it is above 375 degree Celsius, and the pressure will be above 220 bar. 220 bar means what? The pressure and temperature will be above critical temperature. So it is quite impossible to compress this saturated liquid up to this point, 0.2. So it seems impossible. So therefore, let us yes. So the latter case, the cycle B, where we are solving two problems, but the problem is that the compression of saturated liquid at very high pressure exceeding 222 megapascal, that is quite impossible. So it seems that the Carnot cycle is not possible. If we are going to solve one problem, so another problem arises, like this one, that if we are solving the problem of compression of wet vapor, so another problem arises that the compression of saturated liquid up to a pressure, infinite pressure, almost infinite pressure, we don't have any idea what is the pressure. So it means what? But if we are going to solve one problem, another problem arises in the Carnot cycle. Therefore, this Carnot cycle cannot be realized in actual practice. Therefore, let us consider another cycle, the simple cycle, that is, let us allow the vapor the process 4.1 to condense up to the saturated liquid. Once the vapor is saturated to condensed to saturated liquid, now this can be compressed with the help of simple pump up into the boilers. So, but in that case, the cycle will not be Carnot cycle, because now the cycle will not be a Carnot cycle, because we are compressing. The heat addition will not be at isothermal, but this will be at isobaric. So now this, let us modify the Carnot cycle using the concept of what? The condensation up to the saturated liquid level. So let us think that here the boiler, turbine, and condenser. Condenser, that is basically a heat exchanger. So here the simple rectangle inside the TS diagram was the Carnot cycle. Since the Carnot cycle is an ideal cycle, so it is obvious that the Rankine cycle will have somewhat less efficiency, but this Rankine cycle will be, this can be achieved or realized. So we are allowing the condensation of steam up to saturated liquid level, and now this saturated liquid is pumped to the boiler. So the process 1-2 here, you are looking at the process 1-2 is the pumping of saturated liquid into the boiler. So after in the compressor, so it will require some little work, because liquid, saturated liquid, say specific volume will be quite less than the volume of saturated vapor. So at state 2, the liquid enters the boiler and heat is supplied in the boiler. So this process is not reversible isothermal, but this process will be reversible isobaric. So process 2-3 will be the reversible isobaric heat addition in the boiler. So in this process 2-3, we are supplying heat reversibly in the boiler, and high pressure, high temperature steam is generated. So this steam can be expanded in the turbine either at the saturated state or the superheated state, or at the wet vapor state. So if we are expanding this steam, the process superheated steam 3, so process 3-4, so we are seeing that the expansion of superheated steam. So in that case, what is happening, that this is not rectangle, it looks like somewhat horn. So it means what? There will be irreversibility associated with this process. So its efficiency will not be as high as Carnot cycle. Its efficiency will be quite low. So there will be destruction of exergy or available energy. So since we are deviating from the Carnot cycle, therefore its efficiency will be quite less than the Carnot cycle. So suppose this cycle can be realized in 3 ways: the expansion of superheated vapor, expansion of dry saturated vapor, and expansion of wet vapor. So if we are expanding the wet vapor means what? That in the solid liquid vapor dome. So in that case, the dryness fraction will be quite low, so that is not recommended. Even if expansions take place from saturated vapor state, so in that case also the dryness fraction will be quite low. Therefore steam is superheated, so that the dryness fraction or the quality will be higher. So quality below 85% is not recommended. Therefore it is always recommended to superheat the steam in the boiler, the superheater section. So after the superheating, it is supplied to the turbine, where it is expanded according to the configuration of turbine, reaction turbine or impulse turbine. So after the expansion in the turbine, this high pressure, high temperature steam expanded in the turbine, and the work is developed. So this work is utilized for the either rotating, generating electricity. For any purpose you can use this work. So after expansion in the turbine, this process 4. One more thing, we can expand this process. We can carry out this process, process 3-4, the expansion in turbine, up to atmospheric pressure or below atmospheric pressure. If we are applying condenser, then we can expand this up to below the atmospheric pressure. Otherwise we have to expand this process, process 3, 0.4 will be the pressure will be at 0.4 will be at atmospheric pressure, means the temperature will be 100 degrees Celsius. In that case, the efficiency will be quite low, because since we know that the efficiency of the cycle will be the directly proportional to the highest temperature. If higher the temperature T3, the higher will be efficiency, and this T4 should be as low as possible. So T4, if we are expanding up to atmospheric pressure, T4 will be 100%, so efficiency will be quite low. So to improve efficiency, what we will do, we apply vacuum chamber, that is called condenser, where where the steam is condensed. So here in the condenser, what happens, we apply a air suction pump which suck air from the space. Therefore the condenser, the pressure inside the condenser will be below atmospheric pressure, 0.2 bar, 0.6 bar, like this. So therefore the expansion process 3-4 will be carried out from boiler pressure up to condenser pressure. The condenser pressure will be below the atmospheric pressure. Therefore it will increase efficiency. So in the condenser, what will happen? The steam, the low pressure, low temperature steam enters the condenser, where it exchanges heat or it loses heat and condenses to saturated liquid. And this condensation is allowed, and steam is condensed to saturated liquid water at state 1, and this liquid water is again pumped to the boiler by process 1-2 by consuming some work, W pump. So therefore the cycle is completed. So in this cycle, what will happen? The process 1-2 is the reversible adiabatic pumping. Process 2-3 is reversible isobaric heat addition in the boiler, and process 3-4 is the process 2-3 is reversible isobaric heat addition in the boiler. Process 3-4 is reversible adiabatic expansion in the turbine, and process 4-1 is reversible isobaric heat rejection in the condenser. So in this cycle is the Rankine cycle. It is quite different from the Carnot cycle, where Carnot cycle consists 2 reversible isothermal processes and 2 reversible adiabatic processes, while Rankine cycle consists 2 reversible adiabatic processes and 2 reversible isobaric processes. So the isothermal processes are replaced by the isobaric processes in Rankine cycle. The remaining 2 processes, reversible adiabatics, are same in the Carnot cycle as well as in the Rankine cycle. Okay. One more thing, that the process 4-1, the heat rejection is also, this can be, we can say that this process 4-1 is isobaric as well as isothermal, because this phase change occurs at constant temperature. Therefore the process in condenser is also isobaric as well as isothermal. Okay. So this is the simple Rankine cycle, but this Rankine cycle will have lower efficiency. Therefore there are certain methods by which we can improve its efficiency. How its efficiency can be improved? Let us see. So let us first consider the analysis of Rankine cycle. Since the Rankine cycle is an ideal cycle consisting 4 processes, 2 reversible isobaric and 2 reversible adiabatic. So just apply the steady flow energy equation across the various components, and we'll find the work output and work output, heat input and heat rejection, etc. So in the ideal Rankine cycle, let us consider the pump. The pumping is process 1-2. So this process involve the pumping of saturated liquid into the boiler. One more thing, let us first discuss that for the analysis of Rankine cycle, what we have to have is, we have to find the enthalpy at all the corners, means at enthalpy at 3, 4, 1, 2. So we have to find enthalpy at all the corners. So it is very easy to find enthalpy at 0.3. That is what is 0.3? 0.3 is the turbine condition of turbine inlet or condition of boiler outlet. Boiler outlet means the steam generated in the boiler at the condition. So this is very easy to find. by superheated steam table. Generally steam is generated is superheated steam, so we will go to the superheated steam table and we will find the enthalpy T3 H3. So once we find enthalpy H3 and enthalpy H1 is also very easy to find, because since what is the state 1? State 1 is always saturated liquid at condenser pressure. So we can easily find the enthalpy H1 by looking at the saturation table, at condenser pressure. So this is always HF. H1 will always be HF at condenser pressure. One more thing, since condenser pressure is very low, therefore the volume, saturated volume, liquid of saturated liquid, the volume of saturated liquid will be very low, 0.00101, like this. Therefore, and the volume of saturated gas or saturated vapor, is quite high. Therefore, we can neglect the work involved in the pumping, because the pump work is, if the pump work is in the order of 2 or 3, and turbine valve work will be in the order of thousands, therefore the turbine work will be much greater than the pump work. Therefore pump work can be neglected. Once pump work is neglected, therefore H2 minus H1, this pump work will be H2 minus H1. This will be equal to what? 0. So once pump work will be equal to 0, therefore H2 will be H1. So H1 can be found at HF. Value of H1 will be HF at condenser pressure. Therefore H1 will be equal to H2. So this can be easily found. H3 can be easily found. Therefore, what is H4? So to find H4, what we'll have to do is, first, since process 3,4 is reversible adiabatic, so since in reversible adiabatics, so if you recall the second Gibson equation, TdS equal to dH minus VdP. Therefore, if TdS, so since reversible adiabatic, the process 3,4 is reversible adiabatic, therefore TdS equal to 0, therefore dH equal to VdP. Therefore, we can find H2 minus H1 will be equal to what? VdP. So V into delta P. Therefore, the pressure difference means the pressure, the difference of pressure between boiler and condenser. One more thing, this pressure is always in the bar. Therefore, we have to convert it into the Pascal, that is 10 to the power 5 divided by 1000, so that to make it in kilo. Therefore, this pump work H2 minus H1 can be written like V into P2 minus P1 into 100. So this will be quite low. So for low pressure cycle, you can always neglect just by writing neglecting pump work. For low pressure cycle, neglecting pump work, you can always neglect the pump work. Therefore, H2 will always be equal to H1 unless it is asked. So what is the heat addition in the boiler? So this is simple, since this is constant pressure heat addition, therefore just apply the steady flow energy equation for the boiler. Process 2, 3. So once you apply a steady flow energy equation for the boiler, you will find that there will not be any change in kinetic energy as well as potential energy. Therefore, the changes in kinetic energy and potential energy will be equal to 0. So, and one more thing, that there will not be any work involved in the boiler. So the only heat input and enthalpy will remains in the equation. Therefore, the heat supplied or Q in will be equal to the final enthalpy minus the initial enthalpy. So S3 minus S2. So just by applying the steady flow energy equation for the boiler, you will find the heat input in the boiler, that will be the equal to change in enthalpy of the water, means enthalpy of steam minus enthalpy of water, H3 minus H2. Okay, for per kg of fuel. But once again, just for turbine, let us apply the steady flow energy equation for the turbine for process 3-4. You will find that again here in the turbine there will not be any change in kinetic energy and potential energy. Therefore, and there will not be any if turbine is insulated. And since we are discussing here the ideal Rankine cycle, ideal cycle, so the process 3-4 is reversible adiabatic. So the process is reversible as well as adiabatic. This means there will not be any heat transfer. Therefore, there will not be any heat transfer. There will not be any change in kinetic energy, potential energy. So in the equation only W and H enthalpy terms remains. So therefore, work output jo hoga, that is the work output will be equal to the initial enthalpy of the steam minus the final enthalpy, that will be H3 minus H4. So the work output or turbine work will be H3 minus H4. So for the condenser, the enthalpy, low pressure, low temperature steam enter the condenser, where it condenses by the rejecting heat to the atmosphere. So in the condenser, let us apply just applying the steady flow energy equation, you will find that there will not be any heat transfer, there will not be any change in kinetic energy, potential energy. So therefore, and there will not be any work involved also in the heat exchanger, the condenser. Therefore, the Q out या फिर ऐसे कह सकते हैं कि heat rejection will be equal to H4 minus H1. So what will be the thermal efficiency? Thermal efficiency can be written like net output upon the net energy supplied to the system. So what will be the net output? So this can be written like Q in minus Q out upon Q in, or 1 minus Q out upon Q in, or simply we can say the W net. What is W net? Since this is a cycle, so according to the first law of thermodynamics, summation W equal to summation Q for cycle. So W T minus WP will be equal to Q in minus Q out. So we can say W net upon Q in, or 1 minus Q out upon Q in. This is the efficiency. So this efficiency can be written like in the terms of enthalpy. So 1 minus what is Q out? So H4 minus H1 upon H3 minus H2. Once if you are neglecting pump work, therefore H2 will be equal to H1. So you can use H1 instead of H2. So therefore we can find the enthalpy, since we can calculate the enthalpy at each corner with the help of steam table. So we will find the efficiency of the cycle, thermal efficiency of the cycle. Thermal efficiency of this cycle will be quite low, not as high as Carnot cycle, because since we know that this cycle is the heat addition and heat rejection are not at isothermal but isobaric, therefore its efficiency will be quite low. Once again, this horn should be as short as possible. Higher horn indicates the higher deviation from the Carnot cycle, therefore there will be the difference in the Rankine cycle. So let us consider how the efficiency of Rankine cycle can be improved or as compared to the Carnot cycle. So let us discuss those things. So this is remaining numerical. We can solve if time permits. We will discuss how to solve the numericals of Rankine cycle. This is quite easy numericals. So thermal efficiency, how the thermal efficiency can be enhanced. So to enhance thermal efficiency, since we all know that the efficiency of a high efficiency of a cycle will be 1 minus TH minus TL minus TH, where TL is what? The temperature of heat rejection, and TH is the temperature of heat addition. So to increase the efficiency of the cycle, we have to increase the TH. So TH should be as high as possible and TL should be as low as possible. So lowering the condenser pressure. So to reduce TL, what we will have to do is, first case, let us consider the first case, just lower the condenser pressure. By lowering condenser pressure, the temperature will automatically be reduced. Why? Because since we know that this process 4.1 occurs in the condenser, means the condensation of steam. So since the temperature of steam will correspond to the saturation pressure of saturation pressure of the steam. So if we are reducing the pressure, it means what? We are reducing the temperature. So this should be as low as possible. But this is there is a problem that we cannot reduce the pressure below the pressure corresponding to the saturation pressure corresponding to the atmospheric temperature. Therefore, the minimum temperature of heat rejection cannot be lower than the temperature of atmosphere. So this is the limitation. So we cannot reduce this temperature below the atmospheric condition. Another thing, just increasing T3. So this increasing T3, since we all know that this zone is called superheating zone. So this process is also called superheating of steam. So this is always recommended to superheat the steam. So by superheating steam, what we are increasing the efficiency as well as improving the quality or dryness fraction. Just see here, the quality or dryness fraction line or ideal expansion line shift towards the right side. So if ideal expansion line shifted right side, it means what? The quality is always improved with superheating. So superheating is always recommended. Superheating increases thermal efficiency as well as the quality of the steam. But there is a limitations of superheating, because since the materials, since materials has certain limitations that we cannot we cannot increase the temperature beyond a certain level, because the metallurgy doesn't permit to increase the temperature beyond certain level. So that is the maximum permissible limit. Otherwise, we should increase the temperature as much as possible, so that we can have higher efficiency as well as higher dryness fraction. So another thing is, after that, we can increase the pressure by increasing pressure. Let us see, by increasing pressure, so the heat addition at higher temperature improves. So mean temperature of heat addition, or we can say the average temperature of heat addition, increases with the increasing pressure or operating pressure or boiler pressure. So by increasing optimum boiler pressure, what is happening? Let us see. If you are increasing boiler pressure, therefore the mean temperature of heat addition increases, but the ideal expansion lines shifted towards the left. Therefore, if you are increasing the pressure of boiler pressure, so it improves the efficiency of the cycle. But the problem is, the ideal expansion line shifted towards the left, therefore the quality of steam decreases, or we can say dryness fraction of steam decreases, or we can say moisture content of the steam increases. So this is dangerous, because moisture content above 15% is dangerous. It will corrode and erode the boiler blades of the turbines. Therefore, there is a limiting pressure. Above this pressure, we cannot operate the boilers. Therefore, if we are using the pressure, therefore, if we are using pressure higher than this optimum boiler pressure, so the dryness fraction value comes below 85%. That is not recommended. So, but if we are increasing the pressure, so its efficiency increases. So if we want to increase the efficiency further, so we use the boiler pressure above the optimum pressure. So in that case, what will happen? The dryness fraction value decreases. Therefore, we are using another cycle that is called reheating cycle. So what is reheating? Since we are increasing the boiler pressure beyond the optimum pressure, therefore if we are expanding steam from state 3 to condenser pressure, so what will happen? Dryness fraction will comes out like 0.6, 0.5, 0.7, like this. Therefore, this is not recommended. So therefore, what will happen? So in this case, the expansion is done in more than one turbine. So in this case, we are having two turbines, low pressure turbine and high pressure turbine. So once, let us discuss here, the steam is generated in the boiler And the process 2-3 is what? The steam generation in the boiler, isobaric heat steam generation in the boiler. In this case, what will happen after the state 3? This again, why state 3? Why we are not increasing the temperature beyond 3? Because metallurgy doesn't permit. Otherwise, we will have increases the temperature beyond T3. So T3 is the limiting condition. We cannot increase the temperature beyond T3. Therefore, what will happen? So at T3, we supply the steam to a turbine that is called high pressure turbine. Why it is called high temperature turbine? Because the highest pressure steam enters in this side in this turbine. So the high pressure turbine, the expansion occurs up to some intermediate pressure, that is optimum pressure. This is approximately 20 to this P4 will be approximately 20 to 25%, 20 to 30%. So the optimum condition is this. So the steam expanded up to some intermediate pressure. After that, it again enters the boiler and again superheated up to the initial. Either initial, it is not always recommended to. It is recommended to superheat it at initial, matlab T maximum, T5, T3, but sometimes it is somewhat lower than, even lower than the T3. So it is superheated again in the boiler and again supplied in the low pressure turbine and expanded reversibly adiabatic up to the condenser pressure. So in this case, what will happen? If we are increasing the boiler pressure beyond optimum pressure, boiler pressure is beyond optimum pressure. In that case, we cannot operate. So this cycle will not be feasible. We can, but if we are using reheat, so even this cycle can be realized in actual practice. So, but in this case, what will happen? We are using more than one turbine. So it increases the capital investment, but the output will be quite higher, because let us see the expansion of steam from 3 to directly from state 3 to condenser pressure. So in that case, the output will be whatever, like 5 6, that will be equal to the 5 6. But here we just see that instead of this, we are losing. If the expansion is not up to condenser pressure from 0.3, expansion is not up to condenser pressure, so therefore we are losing somewhat, we can say, work. But instead of 4 and 6 dash, like suppose this is 4 and 6 dash, instead of this tiny work, we are having slightly higher work. So in the reheat cycle, the work output will always increases. The work output always increases, and efficiency marginally improves. Efficiency improves marginally, but this marginal improve in efficiency always also come with the feasibility, because this cycle is feasible and original cycle was not feasible. Therefore, the reheating, again, and one more thing, it will require a smaller condenser for the same output. It will require a smaller condenser. Again, specific, therefore specific steam consumption will be quite lower than the original cycle. So specific steam consumption means what? To produce per unit what? 1 kilowatt hour produce करने के लिए कितना steam चाहिए? So that will be quite lower. This should be as low as possible, so it lowers. Again, efficiency improves. So this reheating improves the cycle performance, like the net work output, or we can say the capacity of the plant increases. Also, it requires larger investment than the original cycle. One more thing, the reheat cycle, and again the regeneration cycle. What is regeneration? So in the regeneration cycle, what will happen is, so the expansion of the turbine, expansion of turbine is not up to the condenser pressure, but in between intermediate pressure, some intermediate stages, we bleed some steam and mixes with the steam, mixes with the feed water. This is the concept that we are we are reducing the heat addition at lower temperature to improve the mean temperature of heat addition. Like this, we are, suppose in this simple cycle, what is happening, we are supplying heat from state 2, but here what is happening, we are bleeding steam. So this bleeded steam, we are bleeding steam at 6, and this bleeded steam mixes with the saturated water at state 2, and this improves, this heated the water at state 3. Therefore, we, from process 2 3 is eliminated by the bleeding of steam. But this process also requires the bleeding of steam. Therefore, the special type of turbines are employed for this regeneration, and this type of turbines have several taps. From these tapping points, we bleed steam, and this steam goes to the heaters. Heaters can be of open type and closed type. Open heaters are the heaters in where steam and water both mixes together and attain a certain temperature, while closed heater is like a cell and tube combination, where water flows in the tube and steam in the cell. Therefore, this is also called drip type feed water heater. So the heaters, in the heaters, what happens, we are heating feed water with the help of bleeded steams, and in the ideal conditions we heated this feed water up to the saturation state. Therefore, it it reduces the heat addition at lower temperature, and it improves, or it increases the mean temperature of heat addition. Therefore, it improves the cycle efficiency. One more thing is that by regenerative cycles, since expansion of steam, 1 kg steam, since 1 kg steam enters the turbine, but at the condenser, so I think we will discuss in the next class. Okay, if that I think time is over, we will discuss in the next class. Huh?